you all use more or less of these devices with more or less of automation. But if you think about automation, you have different things in mind. Nowadays, flying taxis, autonomous cars, or even home automation, where the light is switched on following you on your way to your office. But automation has different levels, and you will see that even these small devices have a lot of automation in it. And I would say that automation is also something like the king's discipline in information technology. So we will have a look now into the subject of automation. Welcome. So, welcome to this add-on lesson of my lecture series about computer science. Today we want to talk about automation. Automation is everywhere. So in factories, people are afraid of because maybe it costs some jobs, but there are also additional chances. And for computer scientists, and especially for programmers, there is a lot of work to do there. And especially, for example, in my field with the radio telescopes, all of our radio telescopes run autonomously. And autonomy means that everything must process without any access or touch by a user or an operator. And therefore, there are a lot of things to do, and I want to show you today my view on automation. So what I think is automation, in my opinion. So today we want to talk about the following things. So first of all, I want to explain what is automation. So what is automation in an encyclopedia? And then I want to explain what I think is the main part of automation. So what are the elements, the units of automation? Like here, the hardware driving, the controlling, the failure management, the planning, and the user interfacing. And then let's have a look into a special field of automation, which you already saw in some cases in combination with unit tests. But especially here it is very important because all of the things, especially when or if you have access to humans, so if you have to protect humans, then you have to do a lot of these things, simulations. So let's have a look into the subject of automation. So automation is defined in the German industry norm as the preparation of an environment so that it works partly or completely autonomously without any interaction of a human being. So what does it mean? You have on the one hand the incoming products or materials, so the also input, which is then processed in a process. So you have a production, you produce something new, and then you get a new product, an output, a resulting good, something like that, which is produced within this process. As it is not only valid for products, it's also valid for data, for information, and for other workflows. This means that we take it as input and output, and you can modify or change the process by incoming control settings. These variables define the next steps. They define also the quality of the next steps, and that you can check if everything works correctly. You have also measures, which are matrix parameters coming from the process, telling you about the quality, about the progress, about all of these monitoring things. And therefore, it's the feedback from the process. So this means that you will always have these scenarios. If it is a cleaning robot, or if it is a completely autonomous radio telescope, or a robot in any factory, it's always the same principle. And therefore, if you think about automation, you will see that there are a lot of different levels. As I said in the first words, that if you think nowadays about automation, you directly have in mind these autonomously flying taxis or whatever. But even a small heater has a lot of automation in it. It switches on and off according to the temperature, and for example, it turns left, right autonomously, and it can be used for the heating without any interaction. But it's based on electric and mechanical components. So you have different levels, and therefore you have also different levels of tasks to do. If we start with the lowest level, this is this manual processing, so there's no automation at all. So this is what we usually had in factories. And then you can change to the so-called batch processing. What does it mean? In the batch processing, you have still a lot of human interactivity, but in factories you have these pipelines, so that you have different steps and the people work at these different steps. So it's already some kind of automation, because it's already that the people are supported by equipment. Then you have this assisted processing. This assisted processing means that the, let's say, robots help you. They take over the work from the humans, and they do these jobs autonomously. They have already to protect humans, and these assistants can go quite far. For example, it can also support humans in this way that it carries heavy equipment or something like that. And this is a real advantage for the humans and also for the processing. With this assisted processing, you can also combine then a decision-supported processing, so that not only the special tasks are supported and assisted, it can also be that the next decision, so for example, which pipeline is used, or which steps will be at which pipeline, so that you optimize the whole processing. This can also be done autonomously or planned by a computer program. The next step in my hierarchy here is that you have a predefined automated processing. So all of the steps are automated, but it's completely clearly predefined, which means you have a clear schedule and you run step by step through the schedule, and you have almost no human interaction anymore. And then the next step and the final step in my hierarchy is that you have a self-organizing, self-adapted or learning processing. So this means you have artificial intelligence, and you work on, or the artificial intelligence works on the problems itself. So there's almost no human being there. So for example, a self-driving or autonomous car needs a lot of these things to detect pedestrians and things like that, and that did not always work. They not always works, you see in the daily news. Okay, so you have the change from the human intelligence to the artificial intelligence, which means that autonomy is the lowest here, so no autonomy or automation, and autonomy becomes more and more into this direction. And this also means that the interactivity is reduced. For example, for airplane. The huge airplanes like the A380 cannot be used without computers. So the crew has no direct access to the controls. Every control which is entered goes through something like an autonomous or automated process, and is checked if this airplane is at the moment able to do these activities. So therefore the interactivity decreases here. On the other hand, it can have the idea that the complexity increases, and therefore the human responsibility decreases. So this means that you have to define also things like who is responsible, and in cases of law and order, who takes over the responsibility. For example, if a car, like a self-driving autonomous car, crashes into a pedestrian. Okay, so there are a lot of facts, a lot of things. We don't want to take care on these law and order things. We just want to take care on the computer science aspects, and therefore we want to have a look into these steps, what is necessary for automation and autonomy. So therefore, for me, there is a big change or big difference between automation and autonomy, which means that the degree of independence and autonomy is really high and without failures, so that no human has to interact. So automation is everything where, for example, complete tasks are taken over and people don't have to take care of it. So like the cleaning robot, this is automation for me. And autonomy is that also decisions are driven autonomously. So no user interaction or intervention is necessary anymore. So even nowadays with these autonomous cars, this is not reached at the moment. But in these cases, like in the airplane, intervention should always be possible. So the humans who are in the way to control something should be able to at least interact with the system. And therefore we directly come to my units, or my defined units of automation, or at least then also autonomy, the implementation units, and I define them as hardware driving, controlling, failure management, planning, and user interfacing. And this is defined, I found this in one paper, and I adapted it to a situation which is based on my field of work in geodesy, so for a laser ranging system. So you have the laser ranging system. In this case, you have incoming data information or products, so which satellites are available, where are the positions of the satellites, things like that. And then you produce outgoing products, which are the observations, so the distances to the satellites or things like that. And to do this autonomously and to do this with these units, again with planning, controlling, hardware driving, failure management, and user interfacing. So these are the center parts. So hardware driving and controlling is a very essential, close together thing. And then the failure management, which must be at least a beep or something like that, which tells you that an alarm is or alarm situation is given. So all of these central parts are really essential. And then of course you have to do the planning. This can be done by humans or also autonomously. And then also here the user interfacing. And I call this, like in this paper, autonomous production cell. So what is an autonomous production cell? An autonomous production cell controls selectively things to solve autonomous functionality. Again, planning, controlling, user interfacing, hardware driving, failure management for specific tasks. And this is for the whole production. Okay, so they decompose a complex autonomous production into small pieces, into small cells with self-similar small and manageable units, and keep the performance and characteristics of the whole cell for their smaller tasks. So you can have a complete view, always with these 5 parts of planning, controlling, interfacing, and so on. And then this huge view can be split into small pieces so that each single task in this complete autonomous production cell can be seen as the same setup again for a dedicated purpose. Okay, so each cell is something like a copy of the central control facility and keeps itself alive. So it can be a hierarchical structure, it can be just one cell, or it can be a hierarchy, so that you always have a combination of cells in such hierarchy. So we did this for itself for some of the observatory tasks, especially in laser ranging, but also for observations with radio telescopes. And therefore, I want to take a look into these special things like hardware driving, controlling, and so on. So what is hardware driving? Hardware driving means we focus now on the real connection between, let's say, the software part or electrical part to pure hardware, like this gear here, or a huge motor or servo system. And there's a lot of work to do, and let's have a look onto this lowest level, and I would say this is regulation. So it's not this what we think about automation. It is already automated, but it's more or less regulation. It regulates something according to incoming information. So in this case, the simplest version is a heater. So you saw it in the intro. So it's a power supply, you have a switch, and you have a heating. So if you have it in this way, it's completely manual. So you have an actor. This actor is closed, and then the heater starts to heat. Okay, so it becomes warmer and warmer, but you have to switch off again. So this is an on-off actor. This is the simplest version of an actor. On the other hand, you can have, of course, something like adjustable resistance switches, so that you have a possibility to do something like this. So I'll jump to here. For example, the heating or the power, the current which goes through it, is the highest as smaller the resistance is, and then you can regulate how the heating or how powerful the heating is. So therefore you have adjustable actuators and you have on-off actuators. Let's focus on to these on-off actuators. These on-off actuators are at this point manual. So you have to switch on or you have to switch off. But with a simple equipment, with a mechanical hardware, you can easily change this. So you take a bimetal switch and then you have an actuator. This actuator can now be used for the heating detection. So for example, the switch is closed, the heating starts, so it becomes warmer and warmer, and then this bimetal part detects the heat, and then it can switch off according to the temperature. So what we have now is a simple sensor. It's a simple sensor combined with an actuator, and in combination with this you have something like a feedback loop. So the temperature climbs up, and at the special temperature it switches the circuit off. So we have a sensor combined with an actuator, and this defines a feedback loop. So this is the simplest elementary form of automation. In this case, it's more what I would say regulation, because it detects something and it reacts on it, but it's the simplest form of automation. So this is the low-level version of automation. In principle, what you have here, this bimetal switch, is a mechanical part combined with electrical switch and things like that. So you can have mechanical, electrical, electronical regulation at this point. So it's really, let's say in most cases, hardware. And this is also what you have in very complex systems. So you have here on the one hand the physically controlled system, so the thing which you want to regulate. Okay, then you have this part here, these actuators. The actuators are in principle a conversion from special voltages, currents. So you have a converter from a digital to an analogous signal, and then you have something like a servo driving system which matches to it, and then you have an actuator element which controls the physical device. And then on the other hand, you have the sensor. So the sensor detects this again, and then it can see that there are some test circuits, and these test circuits detect this physical equipment and converts it, so it's something like a converter, into a digital signal again. And this is the feedback loop to, let's say, a microcontroller. So in the first sample we just had hardware, we just had electronic or electric, and in this case now we have already a microcontroller processing these things. And then you have a communication to control all of these pieces. Okay, so this is, look at it again, so I will show it again. This is the basic part of communication with a physical device. We have on the one hand the physical electrotechnical part, so the physical controlled system with all of the circuits to convert between a digital situation and information to a physical, mechanical or hardware-based situation. And on the other hand, we have the information technology, the engineering for the computer science stuff. Okay, so therefore let's have a look into a small sample for that. We want to do the regulation of a wind sensor, and we want to do it already with a small microcontroller. So what we have here now is a microcontroller, here in this case an Arduino, small microcontroller, and on the other hand we have a wind sensor. So we have this wheel here detecting the wind, not the direction but only the wind speed, and it detects it with a very simple sensor. It's a read contact, and this read contact is uses a magnetic part, this magnetic field switches here the sensor and produces something like pulses, and these pulses can be counted, and if you have these counts you can convert it to the situation of, let's say, a wind speed. So you can directly convert it to according kilometers per hour or meters per second. Okay, what this sensor also has is a temperature sensor. So with this sensor you can measure the temperatures, and you can use it for the switching of a heating. So for example, if you have a winter situation, so that you can melt down snow or ice from the sensor. So what do you need now? You have on the one hand the IT, and on the other hand you have the hardware. You need something like a conversion, and in this case we do it with a very simple circuit. We just use a few resistances and a few capacitors, things like that, or transistors or MOSFETs like here. So what we need is, for each sensor, for each actuator, we need such a converter. So for example, for the first sensor, which is this read, we need this gates here, this circuit. For the temperature sensor, we need this here, and for the controlling we need the driver. Okay, so these are our transducers in principle, and this is our driver for the different currents. Okay, so here the heating is connected to the same voltage, so therefore it would not be necessary to have this, but usually you have different voltages here, so that the heating runs on a higher voltage, so that you have to convert the normal voltage, maybe on 5 volt, to this high voltage. So what you get then is a mechanism which can be programmed, and also you can get interaction to this so that you can send in information or you can read information from this equipment. Okay, so what is now the important thing? Here runs a program, so software, which reads from the sensor and converts it to commands or switching pulses or switching situations of the heating, for example. So it counts the pure data which are required with these pulses, and it also regulates the additional parameters like the heating. So for the heating, on the other hand, I have to jump to here. So on the heating, on the other hand, you have to think about special behaviors. So like this hysteresis, so that, for example, the heating switches on at 0 degree, but it switches off later at higher temperatures, like at 1 or 2 degree. So that you avoid this always switching on, switching off if the temperature is not stable and just toggles around 0. So you have special periods where the heating is switched on, and you have special periods where the heating is switched off. And the switching on happens at 0, for example, and the switching off happens at this higher level. So you have to think about this in your program, and you have to deal with this. And you have this conversion so that you can control with your IT the hardware on the other hand. Usually you not only control one hardware device. So you have this piece of equipment which I explained. You have this several times for different things. So for example, if you have a meteorological station, you have a lot of these sensors and all operate in this way. And then you have a higher level equipment like a programmable controller, like a logic array or a logic controller or industry PC or a combination of that. You have again communication. So this looks quite similar to what you see here. Okay, so with this microcontroller and the communication, but you have now a higher level communication, and you have also more, let's say, CPU power, more throughput. So what you have here in this scenario is now you still or you again have some feedback loops. So you have a low level regulation loop, you have a higher level, it's still a regulation loop. So here's the difference. So it's a flowing difference. So if you think it's complete automation at the moment here, or if it is just regulation, well, what you have in this explanation is you have this analogous I/O lines, you have these digital lines already here then, and then you have high level buses or communication equipments like serial communication lines or bus systems, and here maybe you have already Ethernet. So from step to step you reach a higher level of automation. Okay, so a higher level, in this case regulation, and you can also already integrate higher level automation decision making. So it depends on, it's a very fluent process. As I explained, this is now the situation of a meteorological station or weather station. So you have again a program, you have clearly defined interfaces to this, which combines already a lot of the sensors. So you not only detect wind speed, for example, again, this heating control and this detection of the current temperature must not be part of this high level part. It can also already be part of this regulation, of this hardware regulation. But for example, if you also want to detect if it is raining and if it is cold, so that you can maybe guess if it is snowing, then you need information from other sensors, and then it can be also part of here. So it depends on really of the developer or on the developer what and where these parts are realized and implemented. So therefore, this was hardware driving. This is the essential lowest level part, and you will the most work is to get this or to design and to write things for this adaptation to the hardware. The next step is this controlling. So controlling, I already told you that controlling can also already happen here in the hardware driving. It depends on the design, but here what I think about controlling is this high level control of a lot of these hardware things. So you're now in a very high level, and here I would say is the automation, the real automation, what you think is automation. Controlling this part, so it's really close connected to hardware, and it's also really close connected to this failure management. So therefore it's a very essential part for the control. And what does it mean? It's exactly what I explained about this automation or about this regulation. It's the same step again. So you have input situations, input signals from sensors, so from this complete hardware. It's not totally the sensor anymore, it's something on a higher level part. You have rules and functions, but higher level rules and functions to interpret and evaluate these inputs and to lead or to guide some decisions and conditional driven decisions. And then you will get a result, you will get an activation, or you will get something which is the output of this device. You should already know something like that, because we had it in our other lessons. Do you remember? You have input, you have something which defines what happens with this input, you have clearly defined steps, functionalities, and you have output, and then also resulting, let's say, movement of this read and writing head. So we have this in case of a Turing machine, of a state machine, so of an automaton. We had this already for the languages, for the detection of languages, but you can use the same principle also for these automation things. Maybe not as a pure Turing machine, because this theoretical construction is not really usable or too, let's say, bulky for real implementations, but the principle is the same. So this idea of using inputs, going through a clearly defined set of states, and then defining outputs is the same. So what do you have? You have something like a loop around this state machine, about these states. You have input, you have also memory. So in the Turing machine you have these clearly defined tapes. So this is the theoretical construction, but here we can use any type of memory. We have inputs from the devices and we produce outputs. So we send something to the device, to the actuators, and we also store something on our memory. So you have a state machine, you have a continuous feedback loop, and then you just follow the steps according to memory situation and the inputs. So this is what we have, and you already saw something like that again in the theoretical computer science part about language theory. We had input, we defined the input with these things. We have these arrows, these edges between the states. We have clear states, we have clear defined end states, and we have then for each arrow here, for each transition, we have clearly defined outputs which tell us what is the action or the reaction on this input. So we have a conditional transition which define all of these runs or paths through our states. So if we do this here, we will always be in a clearly defined state. So it cannot happen that we are in a situation which is not defined. It can be that we will not leave such a state anymore because this transition is not defined, but it cannot happen that we reach a situation which is not defined here. So it's for failure management is essential. So the conversion from this to here, you already had it, or I already showed it to you in one of the samples to program the conversion language or a conversion language. So what you have is you have a while loop, a never-ending while loop, and you have these switch case states, and at each position you have a conditional decision which defines the next state. For example, it tells also the tape or the memory what is the resulting product or the resulting information, so the output, and then it jumps to the next state. Okay, so if we are in state 0 and if we read this, then we jump to here. The same is for a robot. So if this happens, then do this. Okay, so it's a continuous loop, and you can define clearly all of the states. So for real complex systems, the states are much more complex. So what does it mean? For example, for a laser ranging system, we define these states. So this is a decision table. So here are the decisions, here are the inputs to the decisions, and this is the run through these steps. So these are actions which happen here, and these are decisions which are made. So there are a lot of decisions to run through, so that, for example, laser is switched on, that all of the detectors are switched on, that also the detection runs, and that detected hits, so detected laser hits to the satellite, for example, are found, and so you see it's a real complex thing, but in principle this flow chart here is nothing more than a state diagram, and it continuously runs. So you have special end states, you have special situation where it stops. Okay, so this is a sample for a real, let's say, high level complex system. Each of these decisions, each of these things are then a lot of small equipment accesses. So there are a lot of device accesses, there are a lot of pieces of software and hardware, and therefore it's not really simple. Okay, but the principle is always the same, and it still follows this layered system. So we already had this very low level actuator sensor system, so where we have electric things. Then we had this high level programmable logic, and where we are now is this part. So on a industry PC or on a high level computer, we have now a very let's say sophisticated control loop, where we also take care on, for example, to control the timing, so that we don't propagate time or delays from the lower level sensors to higher level decisions, and that we have also higher level detectors if something goes wrong, so like watchdogs or like safety devices, things like that, and that we really protect our data. So this is a loop running all the time with the states, with the state charts, and then we run and control via this way the lower level regulation. So, and this is where it's split between automation and regulation. And this part, so it's, as I said, it's a fluent process. So at this part you have this more or less regulation things. So there is not so much combination intelligence. And here you have this higher level automation. So on the way now, we are already really high automated, but it's a really static process. So what is now the change to autonomy? The autonomy also happens at this higher level part, and it's combined with a learning system or with an intelligence system. So we have to take care of these state changes, and these state changes can be driven or can be implemented with a different solution, like with these systems of neuronal networks or other deep learning or learning mechanisms. So therefore, if you not only use a really static run, if you adapt to different situations or to a learning set, then you can adapt your processing to a specific situation or you can adapt it so that it's really, really efficient. Okay, so what does it mean? The selection of the following state is now made by neurons. It's just a small outlook into these neuronal networks. It's a huge field again, but just that you get the idea. The idea comes from the human brain, so you have something like activator functions. So you have something like a piece of software or equipment where you have a lot of inputs, and these inputs are weighted. So the inputs can be, let's say, adapted with some weights and can also be biased. And then a sum is created so that you get at least one number. So from this, a lot of inputs, and it depends on how many inputs you send in, you get one number, and then you have something which is called activation function, or sigmoid function can be used, which then decides when the output goes to a special level. It can be a binary level, or it can be also a probability or something like that, so that you have inputs and outputs again, and this is more or less adaptable, automatically adaptable. So what happens in this here, you can have different functions, and this is now the special thing where designers for neuronal networks have to look in. They have to use different neurons, they have to use different activation functions. For example, you can use linear with a threshold, you can use binary, so which is just in a special input reaching. If you have a special state, then it switches on, or you can have these logistic functions, so the sigmoid functions, so that you have different possibilities, and now this combination of different neurons, because it's not just that you have one of these neurons, you have a lot of these, and this is also why nowadays this artificial intelligence or neuronal networks are so popular, because now the hardware and the computers are able to do this, to work with a lot of these neurons. So it means that you combine a lot of these neurons. The output of one is the input of a new one, so that you produce something like a brain. Well, it's not really like that. So you define the network, but you can thin out or improve or make more important one of these edges between the neurons. So you have input layers, you have hidden layers which are in the middle, and you have output layers, and then you can drive some special outputs so that you can make decisions like for the selection or detection of signs or something like that. So what happens now is you define a set of inputs and you define a set of outputs, because these neurons, these weights, must be adapted to a given situation. So that the neuronal network must learn, so it must be trained. Never use these sets, and you run through this so that the weights are adapted to this, and then a special input scenario with a special probability will lead to a special output. Okay, so therefore you have now the learning step, and after the learning you have the processing step. With these weights, then new situations are evaluated, and therefore you can adapt to special situations. So for example, you can build something like artificial A's, or you can detect handwritings, things like that. And if you continuously learn, for example, if you use the new inputs for learning, so that if something goes wrong, that you get feedback by users or something like that, then you can always improve the situation. So even with search engines using these neuronal networks, there are people behind detecting if something goes wrong, and they feed in information so that the neuronal network or other artificial intelligence techniques will be adapted again to the right things. Okay, so what you get then with this, and this is now what I mean with autonomy. Autonomy means that decisions are driven by the system, so it's automation with no human interaction. Okay, So therefore you have something like a so-called agent, and this agent takes orders and brings back reports to the, let's say, human or other agents. But what does it do? It uses different sensors, so in these different hierarchies, as a feedback from the environment, and then it makes a perception, evaluation, decision, and control. So here is the, let's say, neuronal network or higher level state chart or state machine, and with this control, effectors and actuators are forced to do some actions. So you have higher level feedback loop, and if you go back to these different levels, so you have the lowest regulation level, mainly hardware, then you have the automation level where you have the state machines and things like that, but there's some human interaction, and then you have this high level autonomy or autonomy. Then this means we have these different levels where you have this different aspects of human interaction and of activations. Very important here, in combination with these two things, is also the failure management. Because if there is a failure, and if you have a completely autonomous machine or autonomously running machine, then it can happen that a failure costs life and or influences human beings, and therefore this failure management is a very essential and closely connected part here. So let's have a look into this failure management, and let's take care on this failure management. It's part of this automation. You see it's here. I put it into the center of this autonomous production cell, and you directly see it that you already maybe have an idea of what failure management is, because if you go back again in our lessons and you watch the state machines again, usually we define something like this error state. Even if we not directly pointed out to this error state, I always explain that each not given situation here, if each not given transition, so a transition which is not possible here, will lead to such an error state. So therefore this is the lowest level of failure management. If you cannot do the transition, go to an error state and stop the machine. Okay, stop. Another thing is that you can again use different levels of automation so that you have a parallel failure control. You see here is the normal feedback loop, and on the other hand it can also use memory and things like that. You have another error or failure feedback loop that checks the inputs from here, so from the devices, and combines it to a logical situation. So you can use fuzzy logic, or you can use neural networks, or you can just use simple state machines, but it drives to an input, and this input is like all of the other inputs which influences this. So it can change the processing, or it can stop the machine, so that it really influences this, but it's just an input from a parallel error control. Additionally, you have of course this already mentioned state machine errors inside of both of this, so that you have controlling of these scenarios. A simple example is here also from my daily business. Important is that errors or quality values for the processing can be converted to a matrix system, so that you get numbers which tell you something about the quality, about the situation, so that you can drive decisions from that. And here we have, for example, in our monitoring system, we have these decisions. So it's a combination of logical conditions, and if this condition happens, you have special alarm levels or severities. In our case, we defined 4 scenarios of severities. So everything is okay, it's green. Situations where we should be informed so that something goes wrong, so it influences the quality of the product so that we will not have the same quality anymore, or warnings, so it means we will not have the product anymore, but we still have no situation where human beings are in danger, for example. So therefore, if we have this warning situation, we can reset special devices, or we can run through troubleshooting rules. The final severity is the highest one, where human beings or the machine itself is in danger. And this always leads to a stop. So we convert input scenarios, so different digital parameters, to scenarios where we can drive decisions, and then we can at least define situations where we have to stop or where we have to run internal troubleshooting mechanisms. So this means we go through these parts here. We define hazards to humans, hazards to systems, hazards to products, or to the quality. So these are our main drivers in our case. And this is the elementary failure management. So here you have another, let's say, state machine, but you will come to situations where you have to stop. And even in autonomous cars, you have this situation. So for example, in some cases you have to stop if you cannot come to a functional result anymore. Let's have a look into the next step, which is the planning. So these three parts are the close things together. All autonomous machines or automated machines need this. The planning is the general schedule for all of these things, and it can also be done with autonomous or with state machines, or it can be just something like a timing. So what does it mean? Planning is the timing for the rest here. So this means that you need a central equipment which plans the complete workflows of all these autonomous production cells. So it's the next layer. Okay, so you have a lot of these small devices, then you have these high level PLCs or combinations of the devices, then you have this high level automation, or also this completely autonomous production, and then you have the next level which controls and organizes the workflow through all of these production cells. And this is especially what you have in this, let's say, equipments for the observation as well. And you can do this again with a state machine, but what you have to think about, which possibilities for a time schedule do you have? So for example, if you have a cleaning robot, then you can decide that it always should start at a special time. Okay, this is already planning. So it always defines a clear but static a priori start time. What you also can do is you can maybe use special sensors if it is possible, and you start the robot only if it is really dirty. Okay, so if your flat is really dirty, and then you have a dynamic, but it's still a priori, so it defines it. The whole processing is the same, but it now adapts it to the situation. Or it can run through the whole house, and at that places where the most dirt is, it will stay longer, and then it adapts to a dynamic situation. And this is what you can do for the planning. You can have a static a priori, for example, once defined by a human being, or you can have dynamic a priori or dynamic real world or real time scenario. So static a priori, as I told you, there's an alarm watch, and it regularly starts the same schedule of tasks. Dynamic a priori means at special time periods you plan the next 10 or 5 or whatever hours, and then you follow statically this path. So you don't think about anymore. You use the current situation and you plan it. So you have a schedule, you have a path through different scenarios, and you run through it. So it regularly starts defined but adapted at a special time period, fixed schedule of tasks, which is fixed for the coming period. Okay, and the dynamic real time is it always takes inputs from the senders, the current situation, and it adapts always the next steps. It decides when to change. For example, here we have a weather situation here, meteorological situation of a cloud coverage, and it decides which satellite is used when, and it always checks. For example, if no hits of returns from the satellites are detected, then it again changes to the next satellite, maybe to this one, and then it always continuously detects it. So it's a permanently check of all parameters, so that current tasks can be interrupted, plans can be changed, and new situations can be forced by new decisions. So these are the steps, and of course users have to know about what happens inside, so in the hardware, in the controlling, the file management and planning, and therefore you need a really nice user interface. Nowadays user interfaces are really important, so we are now here at this part here, so it's part of the autonomous production cell, and nowadays user interfaces are mainly based on web pages. So you will have some kind of special web page, static or dynamic. So in this case, this is the web page for our radio telescopes, or you have also a web page for our failure management system, for the system monitoring, so that you see if there are failures and you directly detect it, at which building, for example, a guard has to go to change, to switch things and to work with it. So these are parallel systems. For example, to the real control, we have this scenario, so that separate error detection is used for the real processes here. In this case, you have to know something about HTML. So this is why I told you something about HTML in one of the lessons before. But and this is what you did not learn in my course. You also will have to use JavaScript, Java, PHP, or SQL, because if you want to connect something like databases, you need this connection language, this interface language. So this is the current state of the art, and also you will have something like apps on your mobile phone or also on your computer, so that you can build up control rooms like this here, which is in Hobart, in Tasmania, controlling several radio telescopes. And usually these things are written in Java, Python, or C++. So you have different clients connecting to this central equipment and also to this central scheduling tool, so that everything runs autonomously, but you can always interact with it with a special degree of interaction. So if you have this, you have to think about how good your automation is, and therefore you have to think about to simulate your programs. You already know something about simulation. We talked a little bit about during the discussion about algorithms and also about software development, and it's very similar to that. Okay, so it's very similar what you find here. And therefore we can use the same principles. So What is simulation? Simulation is the imitation of the operating system, of the operation in a real world process, and we do this in let's say artificial environment, and we check how this real world process acts or reacts over time. And for that we have to use special models. So we have to use assumptions and we have to use special models. So in best case, before I do some theoretical explanations, I just show you some samples. They are based on things like that. So remember, we had this for software development. So the earliest way or the earliest position to do a simulation will not cost too much money, because if you produce already some, let's say, hardware or software, then simulation is quite expensive. So therefore you have to think about how good your algorithm is. And we did this check for the algorithms. So we had this function under test. Now we have the system under test, and we entered the test cases with limit values, with min max values, extreme values, or illegal values, things like that, or random values, so that we see if there are wrong results, crashes, leaks, or something like that. This means that we will have the same classes like for algorithms. Do you remember? Correctness, functionality, or partial correctness, and also compared to efficiency and performance. So it's not only that we test if everything works correctly, we also want to see how efficient our system is, our autonomous working automation is. Okay, so therefore let's have a sample. As I told you, let's look into a sample. So we have the situation of a cleaning pot. So my intro totally comes to here now. We have a room. It's a theoretic room of 100 cross 100 units, and we have a starting position of our robot, and we have a starting direction of our robot. Then we have to define a goal. So the room should be cleaned. So almost all positions should be touched once, and we should not touch maybe positions several times. At least the room should be clean, and therefore we have to define a algorithm and a simulation for this algorithm. So we simulate it without any robot. So we simulate it here in MATLAB or with a MATLAB program, and therefore our task or our state machine is quite simple. We have a starting state, and this is already the state which is kept. So it is kept because each time, this is now the condition, if we reach a position outside of our room, we turn, for example, 90 degrees, or we turn some degrees. So therefore our first attempt is this simplest suggestion. So if there is a wall, turn left. Okay, so therefore let's simulate these things. So let's simulate what happens, and we can do it step by step. So therefore I will directly show the outputs. So this is the small program. The small program defines some initial parameters. So for example, the direction, the starting point, our room, and we also define how fast the steps are going on and which rotation degree which we use. So in this case we start with 90 degree, and then there's a while loop. This while loop continuously runs. So in this case, this while loop is quite simple because it's this state machine. So it continuously runs. It just checks if we're outside of the room, and then we do this rotation. The rotation is done with a matrix, so with a rotational matrix, and then we plot the current position or the current movement. Okay, this is everything. So how does it look like? So if we do this, we have a starting situation. So here we have a starting situation, and then it continues to work to the first position, and it continues to the next position and so on. And then if we reach this wall here, the end of the room, then we turn left. So it continues and continues and continues. And if we watch this, we will see that after a special time period, it will always follow the same way. So our first attempt to clean the room was not really successful. So therefore, what else can we do? In this case, we reach what we already know, which is the halting problem. We don't know when this problem appears, so we don't know after how many steps it will appear. But in this case, our process will never stop because the room is not cleaned, and therefore it will always continue at the same way. So this halting problem you can find in the algorithm lesson. So let's do another situation. In this case, we change the direction and we change the position. And you see that, or you will see that the halting problem also appears, and it will appear quite early. So this is what is difficult to detect when this situation happens. But all of these situations, all of these simulations show you one thing, that this first attempt to always turn 90 degrees is not really a good way to do this. So let's change. Maybe don't turn 90 degrees, let's turn a small degree, like 5 degrees. So what happens now, in principle, is the same. So it will toggle a little bit around this predefined path, but it will never leave this path anymore. But will it really follow forever? So again, this is the halting problem. You cannot say if there will be not a situation that you leave. In this case, it will. There will be not a situation that it will always follow this way. And you can play with these programs a little bit, and you will always see the same situation. So let's bring in more dynamic. So in this case, more dynamic situation means we change the rotation angle. So let's change the rotation angle each time if we bounce against a wall. So let's start with a small rotation angle and then change to larger and change to smaller and so on, so that we turn left and right, and but it always still follows a predefined, let's say, state, and therefore it's clearly defined that you always have a small change in the rotation, and it's not completely free running. Okay, so let's see what happens here. If you run this, you'll see it looks quite nice. So you see there are a lot of different lines, so the number of lines grow, and therefore it seems that now it really works. So if you stop after a special time, it looks quite good. But does it really solve the job? And how fast does it solve the job? So therefore, our simulation at the moment is not good enough. So we now change logically dependent degrees, and we don't know if there is this halting problem again. So if we will always follow the same path, or if it will change so that all of the positions will be touched once. So therefore, we have to change our simulation, we have to change our algorithm so that it does not plot each step anymore. So we want to run 100,000 steps, for example, and we want to see what is the result, how many positions are touched. It should also run the whole simulation, as I said, so that we can change the number of these steps, and each step should be also normalized. So before we had different number of steps, now we just go 1 unit per time unit, so that we have a more realistic scenery, that we can compare different algorithms. We will register all visited positions, so we have to set some markers, and we also have to set the markers if we touch it more than once. So if we visit positions several times, so we have to see this. And we want to show these appearances of, or these touches of different positions and the repeating accesses visually with different colors. And then we want to print the number of visited or not yet visited positions, and also the number of, or the maximum number of repeating visits. So therefore that we get some information to detect. So we need, and this is what I told you with metric, we need some quality parameters which you can really use to evaluate our algorithm. So let's have a look again into our previous logically changing degree algorithm. So let's start with 10,000 steps, and you will see that there are 6,000 or almost 7,000 positions which are not visited, and you have 19 positions which are visited several times. So it seems quite good. So let's increase the number of steps, like here to 100,000 steps. And then what you see here is that the number of missing just decreased a little bit, but the maximum number of repeated visits increases. And with 1 million or with 100 million visits, you will see that the not yet visited positions will not decrease tremendously anymore, but the repeating parts or the repeating positions increase, and therefore this is a clear detector that it will not clean the whole room. So what does it mean? With additional information in this simulation, we see that our algorithms do not work, but we still keep this simple algorithm and we just change it very simple. We do randomized processing. So instead of changing the degrees periodically from -90 to 90 degree, we now completely randomized calculate or do a randomized calculation of these degrees. And what happens is that you see after 10,000 steps you're already much better than what we had before, and already after 100,000 steps almost every position is touched. Why did I make this about sign here? Because each run is different. So it can happen that you have here hundreds of missing positions in one run, but now we have to evaluate in the mean how good it is. But you can reach really good runs, or you can reach or you can get, let's say, not so good runs, but compared to the previous one, this situation is much better. And you can also check or make the situation a little bit more complex. So let's have a look if we put in some furniture. So let's have a look if we put in an additional rectangle and we want to clean also the inside, and we have just one small gate. So in this case we have a gate of 9 units, and you see with 10,000 steps there is not really a big difference to before, and already with 100,000 steps we reach a really good result here. And the great thing is that it even do not change if the gate is just 1 unit anymore. So it's just a very small hole, and you see you have a lot of repeating. So the lighter parts here are repeating visits, but you are with again 100,000 steps you reach a real good result. Okay, if you let it run there, maybe you 500 missing positions, but even with a very small hole here you reach a real good result. And this is why cleaning robots really work. So with just the bumping, sensor, you can reach a real good result. And now you can think about making this scenario better and better and better. But in principle, the simplest automation with about 80 lines of code and with a very simple strategy gives really good results. And this is what I think it's really amazing. And this is what I really like in automation. You can reach a huge step of automation with a very small or with a very small program with a simple idea. So with the simplest ideas, sometimes you reach large results. And with the best plans, sometimes you reach not the real things what you want to reach. Okay, so therefore, this is my lesson about automation. So we saw my specification, my units of automation, which we also realize in the observatory. You see also what I did about simulation, and that small jumps are much better sometimes than big jumps. I hope you enjoyed the lesson, and this is now the last lesson again of this semester. Maybe I have an idea for another one, so the last of the last of the last. So we'll see each other again. Have a nice time, and watch also maybe later on the tutorial.